You mentioned dark matter is perhaps even more mysterious than dark energy.
Okay.
Can you build up the intuition why it's more mysterious? What is dark matter?
Oh gosh, what is dark matter? A, I don't know. B, it's terribly fascinating.
Yeah.
All right. So, first thing, and the most important thing, because I'm an experimentalist, by God, the first thing is, why do we believe there's dark matter? And the reason is that astronomical measurements do not agree with predictions by Newtonian or relativity theory. Galaxies spin too fast, clusters of galaxies move too quickly, and the distortion of very distant galaxies due to the gravitational field of near galaxies disagrees with the prediction from what we see from the observed matter. So there are three very distinct reasons why we are predicting that something is wrong in our understanding of either the laws of physics or the matter budget of the universe. The easiest one to talk about is the spinning galaxies. Now, this is what I'm saying is not unique to spinning galaxies, just easiest to talk about. So, galaxies are observed to spin more quickly than they should if we add up the gravity we see. By all rights, galaxies spinning that fast should blow themselves apart, and they don't. So, what can be the answer? Well, you have the force required for a star to orbit, to move in a circle, and you have the force due to gravity, and they're connected by an equal sign. And the prediction is wrong. So either the force due to gravity is wrong, the force needed to move in a circle is wrong, or the equal sign is wrong. I mean, this is really simple. One of those things is wrong. So, one possibility is simply that Newton's law of gravity, mass times the mass over r squared times a constant, that's just wrong. Another possibility is Newton's F equals ma that we are taught in introductory physics is wrong. Both of those are eminently possible. Over here, maybe we don't understand gravity, or maybe there's more mass than we can see. So these, I mean, it's nice that you can look at this really simply and come up with a list, cookbook of things we can test. And so we've done that. We've gone and said, what are the possibilities? Well, the most obvious possibility is that there is more mass than we can see. There's black holes, there's hydrogen gas that we can't see, whatever. There's something out there. So that was the first thing. So you go and you look, and there's no hydrogen gas because we can see that with the radio waves. That's not it. In the 90s, we went looking for black holes, rogue planets, things like that. Those exist, but not enough of them. That's not it. And so now we're left with there's some sort of matter that we can't see, or we don't understand gravity, or we don't understand inertia. Now, I personally, if you asked me this, I don't know, 25 years ago, I would have said the most likely answer is that we don't understand inertia or gravity. 20 years ago, 25 years ago, that's what I would have said. No problem. However, there have been a couple of observations that have caused me to change my thinking, and I think that dark matter is more likely. One of them is called the bullet cluster. So the bullet cluster, there are two large clusters of galaxies. In these large clusters of galaxies, well, any galaxy consists of a couple of components. There are the galaxies themselves, there is the hydrogen gas that surrounds the galaxies, and maybe there is dark matter. And if dark matter is real or dark matter is not real, you will get different answers if those two galaxies pass through one another. The galaxies themselves should pass through one another, basically not interacting. But the big thing is the gas clouds. So if there's big clouds of gas, as the galaxies pass through one another, the clouds should interact and the gas cloud should stop in the middle and be really, really hot. So then you would see, if there were no dark matter, you would see a cluster of galaxies. A cluster of galaxies is a big gas cloud in the middle. And because the big gas cloud in the middle is much more massive than the galaxies themselves, you would expect to see distortions that we call dark matter distortions in the middle. If, however, dark matter is real, the galaxies pass through one another, the cloud stops. Dark matter doesn't interact with the clouds, so it passes through. In that case, you would expect to see the distortions where the galaxies are. And that's what we see. So that is a strong evidence in my mind. The bullet cluster is strong evidence that dark matter is a real thing. And there is another example, which is much more recent. Dark bullet cluster was a while ago, called the Dragonfly galaxies. There's Dragonfly 2 and Dragonfly 4. These are galaxies that rotate exactly according to Newton's laws. And so the fact that they rotate exactly according to Newton's laws says that whatever's causing galaxies to rotate too fast is not a property of matter. But if you had a galaxy where there was no dark matter, for whatever reason, it got stripped off or something, this is one of those lovely ironies that the existence of a galaxy with no dark matter is very strong evidence that dark matter is real, because you can take the dark matter out. So the DF2 and DF4 also suggests to me that dark matter is real. So now, while it remains possible that we need to modify the laws of inertia or we need to modify the laws of gravity, those are possible still. In my opinion, and now this is Don's opinion, but it's probably the opinion of most of the scientific community, dark matter is likely a real thing. Now, that's great. I've taken you all the way to dark matter. So now you're going to ask me, you're going to say, Don, what is dark matter? I'm going to, I don't know. But I know what it isn't. Okay. I know that it is not black holes. I know that it is not rogue planets. I know that we've done the measurements. We've looked across nearly every mass range for compact objects and ruled them out. So if dark matter is real, it can't be made of those. So then you're left with the idea that dark matter is a particle. And that's what we've thought about. The name for the dark matter particle that we've called for a long time is a WIMP, for a weakly interacting massive particle. And we have spent the last, 30 years looking for them in the various ways. There are 3 ways that we might see dark matter. The direct way, which says that dark matter exists literally everywhere in this room, in our laboratory, and the dark matter is passing through the Earth like a wind, and we put up detectors trying to see those. We have done that, and we've seen nothing.
So we should say we have done that for neutrinos.
We've done that for many different types of dark matter. We just simply put detectors in labs deep underground, and we can see neutrinos in them. It's true, but dark matter would have, especially heavy dark matter, what these WIMPs, they have a different signature. And we've seen no evidence of dark matter interaction in these detectors.
So neutrinos are also weakly interacting and also have mass.
They are.
But not enough mass. So WIMPs are heavy on the M.
Right. Neutrinos are indeed WIMPs of a sort. Now, we have to be careful what we mean by WIMPs. They are weakly interacting massive particles, but we can calculate, and there's just not enough mass in them. It's not it.
Got it.
So we need another form. And we have seen zero evidence of this wind of dark matter through the Earth. Another possibility is you look where you think dark matter might be concentrated at the center of galaxies. And if dark matter exists and there's antimatter dark matter, maybe they annihilate and make photons. And so we look for gamma rays and various other signatures of annihilating dark matter. And there are always constantly announcements of, oh, we saw it, oh, we didn't. Oh, the problem is that way of looking for dark matter is hard because there are other ways of making, for instance, gamma rays like neutron stars and stuff. And you really need to understand the details of galaxies really, really well to believe that. And then the final option is what I do, where we smash particles together at high energy. We try to make dark matter particles. If you make dark matter particles, because they don't interact except via gravity, they escape with your detector. So what you're seeing, what you hope to see, is an event where you collide particles, a dark matter particle escapes and you don't see it, but the recoil you see on the other side because momentum is conserved. So you see a blob of energy on this side, nothing on the other side. Maybe that's dark matter. And that also happens with neutrinos. So you need to understand everything about neutrinos and calculate how many of those you see and then hope you see more. And then that might be dark matter. Again, that hasn't worked. So we've ruled out some dark matter particles. But the problem is the range of space of possible mass, if dark matter is of a particulate form, the range of viable dark matter ranges from something like the mass of an asteroid to far lighter than an electron. and everywhere in between. And we've ruled out some little spots in that phase space, but that's a big range.
Is it really possible to miss a particle the size of an asteroid?
The astronomical searches were not sensitive to that level of dark matter, but then you would expect that there would be some of those in the solar system, and if they're what we think, like asteroids or something, then we'd heat them up and we'd eventually see them. But if they're really like truly dark matter, doesn't interact with matter, which means they wouldn't absorb energy from the sun, so they'd be really dark. I don't know, maybe they're out there. But the only way we searched for them was a thing called microlensing. So if a massive object, you have a distant star, and a massive object passes between that star and your eye, that star will momentarily brighten.
Mm-hmm.
And so you just look for these, what they call microlensing events, and you count them. And you see some, and we did see some, black holes pass in front of stars, and we've seen them, but we just haven't seen enough. And for very low mass particles like asteroids, they just wouldn't make enough brightening effect to see. So there's like a minimum sensitivity of brightening, and that about a third the mass of our moon, is about the sensitivity that we had. So nobody, I think, really thought that these low mass guys were likely. What they thought was more likely they were just unseen black holes, which I thought,
Mm-hmm.
I think is completely reasonable.
Makes
Then when
sense.
that got ruled out, I thought, okay, modified gravity or inertia. Well, now the bullet cluster and dragonfly seems to have ruled that out. So I'm stuck in my head with dark matter seems to be real. And we don't know what it is.
And it makes up a giant percentage of matter in the universe.
It is 5 times more prevalent than ordinary matter.
Wow. This is incredible. This is
incredible.
So fascinating.
And that's why it's cool. So if someone out there is, a young person who wants to get into this, understanding dark matter is a big deal. I mean, it's 5 times more prevalent. The problem is as I told you, if the mass is ranging from an asteroid to far lighter than an electron, if you get on an experiment that looks at one little range of mass, maybe you weren't the lucky guy that measured the right place, And that's one of the reasons why, as fascinating as I think it is, I'm not doing dark matter experiments because, if you make an experiment that searches one mass range, it'll be blind to another mass range.
Mm-hmm.
So what you need is many groups doing all sorts of radically different experiments, exploring all sorts of parameter space. And with all that said, until you see it, there still is the possibility that maybe we don't understand gravity or inertia right. You
Mm-hmm.
can't rule that out.
If there is dark matter out there, you're hoping it's actually somehow detectable.
I mean, I don't know what it is. I think it's cool. It's very, very fascinating. That is one thing I really do hope in my lifetime is understood, because I'd like to know the answer to that.
And that's the thing that you can see a discovery of.
You got to get lucky, though. I mean, you got to look in the right place, whatever it is.
Just imagine.
Or you have to come up with that really cool theoretical idea that everybody's overlooked, which is another possibility. And there are people who are really, really religiously hating dark matter, largely because we've looked so hard for so many years, and the experiments in today's world are 1,000,000 times more sensitive than when I was a starting student, and they still haven't seen anything. And that's why people really hate dark matter. I mean, some of them because they think we should have seen it by now, but, I don't know.
I mean, I'm a sucker for direct observation. Not indirect is obviously also really great, but direct, just imagine pointing your telescope in a certain direction, and because of some artifact of cosmology, being able to directly detect a giant amount of a thing that you could say is dark matter.
Yeah, you would see things orbit it, or it would eclipse things in front of it, or...
Yeah, like in an obvious way. Because some of the stuff you mentioned with DF2 and DF4, those are like brilliant, indirect deductions that there should be something like dark matter. But some obvious, blocking, occluding, this kind of thing.
We did that in the 90s with experiments called Macho, Ogle, and some others. They looked for a black hole that you just can't see, black hole you can't see. It's perfect. It's a perfect candidate for dark matter. And if there's enough of them out there, remember, there's 5 times
Hmm.
the number of stars, which means there's a whole lot of freaking black holes out there. We should have seen them, and we didn't.